bound can be avoided. And we made this in the context of a model of the gauge of anomalous symmetries. So we propose this model, and while building this model, we show how this type, this general type of bound that appears from Wess-Zumino terms can be cancelled and so disappear. So I'll talk briefly about why like vector is so interesting in the past few years. I will specify my discussion to like vector couple to some model current which are anomalous, which means they are broken by chiral anomalies. I will talk about the problem of chiral anomalies and how and UV completion related to them. Then I will show you how Wess-Zumino terms appear in the low energy theory, the low energy effective theory framework, and how these terms are important from a phenomenology point of view. So how they lead to strong constraints on the decoupling and the mass of life vectors. And finally, I will show you our proposed model, which is consists on life vector as a new gauge boson due to the gauging of the vector symmetry on the standard model. So I will show you the field content. In this context, I will show you how the strong back constraint from the demonstrated terms can be avoided. Then I will show you how our model is consistent with the electroweak phenomenology. And finally, I will show you the direct searches of new fermions and how we expected, at which scale we expected this new fermions in our theory. Now, in the first year, major model has appeared, which include a new light vector in the spectrum of. The idea is that a light vector could in principle explain many of the low energy anomalies which are here in these figures, which are, for example, the G's to the moon, and light vector appears to be a good candidate to act as a mediator to Axion. By seeing the plot in the slide, you can see that the hint of the dark matter as a particle with a particle explanation suggests new strongly interacting UV particles in masses at the TeV scale, but as well as the dark matter suggests the presence of new weak interacting light particles. So we have two possibilities. However, in the first year, colliders haven't observed so far any new strong interacting UV particles, and this new result leads to an increased interest of weak interacting light particles, because we can suppose that light particles were undetected by the collider experience because the coupling is so small that we can't observe. However, if these particles are light enough, we can observe them even if they are weakly interacting in other type of experiments which are not LiDAR. Strongly means always in having or then one or like the electrical. Yeah, we for example, in a sample strongly interacting with particles. So in our work, we consider the case of a light vector coupled to a standard mark which is conserved at 3 level, by its program and loop level by chiral anomaly. This type of scenario appears in typically in the main extension of the standard model H loop, when we want to introduce a light vector as a gauge boson for given extension of the standard model. But if you don't introduce new fermions, we obtain that the theory is not consistent because of chiral anomalies. An example is the fermionic number symmetry, which cannot be gauged in the standard model directly because its current is conserved at 3 level, which means that the Lagrangian is invariant under a transformation of the fermionic number symmetry, but the presence of gauge bosons of the W and the hypercharging bosons leads to anomalous breaking of the current. So its divergence is non-vanishing due to characteristics which are explained later in this talk. Now, and when like that covers the non-conserved current, an important phenomenology consequence is that there are some parts of amplitude involving the original mode of the light vector, which are energy enhanced with terms like energy or mass to the square, which means that if you consider processes where the mass of the light vector is small, much smaller than the energy of the process we are considering, this part of the amplitudes, which are energy enhanced, leads to dominant production mechanism in high energy experiments, which can place strong constraints on the coupling of the light particle. So I was talking about anomalous symmetry breaking and anomalous. I mean, anomalous symmetry breaking happens when happens in quantum field theory because from a classical point of view, transformation that leaves invariant the Lagrangian of our theory is a symmetry, or this is not true in quantum field theory because asymmetry can be broken by the anomalous effect, the quantum effect. This is because quantum field theory, to make the calculation, you have to regularize your theory. Then you apply the renormalization method, and at the end for this calculation, you return to the original theory to have a physical prediction. However, when you regularize theory, it can happen that some of the symmetry of the original symmetry are broken. And when you turn back to the original theory, your symmetry is not completely recovered, but there is still a small piece of breaking. And when this happens, we say that the symmetry is always broken. An example is the axial symmetry. For example, axial symmetry transforms axial symmetry. If you have a theory with a Lagrangian, which is invariant under axial symmetry, for example, we deal with a massless lepton, it's variant under this transformation. So from a classical point of view, the axial current is conserved. When you try to do all the loop calculation, you have to regularize the theory, and when you regularize, you obtain that this axial symmetry is not conserved in any regularization scheme you may use. And this leads to an anomalous breaking of the axial symmetry, which is, from a classical point of view, observed. When you go to counterfactor, you observe that this statement is no longer, also no longer. So, chiral anomaly is an example of anomalous symmetry breaking. It's a counterfactor, so it comes a loops. Chiral anomalies arise at one loop level when you consider triangular diagrams involving massless fermion fields inside the loop. We see when these diagrams in which each vertex is related to a gauge bosons or a current coupled to a gauge bosons, you see that if you do all the calculation with a regularization scheme, you observe that on the end, the current related to a gauge bosons is no longer conserved because of the contour effects. So you tell that the divergence is non-vanishing and is proportional to some terms to the fields order, which means that two atoms which were the trace of the Q, A, B, C are the generation, the symmetry generation, symmetry generator of the related to the gauge bosons related to the current. And you see that charge massless fermionic field leads to this anomaly. And the anomaly is called chiral because a vector fermion, vector-like fermion charged under this symmetry leads no anomaly. So it's a difference between the contribution of right-handed particle and left and particle. So a gauge symmetry must be conserved, otherwise our gauge theory is no longer consistent, doesn't make any sense. So we need that, each massless fermionic field anomalous breaks the gauge symmetry. However, if we sum over the contribution of all the fermions of our theory, we must obtain that the anomalous trace, the measure of the current anomaly, must be 0. And this is a fundamental requirement for any gauge theory. And if we try to enlarge the gauge symmetry of our theory, particularly of the standard model, we may obtain that we, with a new large group, we obtain some uncancelled current anomalies. And this is not possible. So we uncancelled current anomalies require new fermions. Otherwise, we cannot have a consistent gauge theory. These new fermions are called anomalous because they are needed to cancel current anomalies. And they are supposed to theory to be E because they haven't seen a new fermions states colliders until TV scale. So we consider them to have masses above 100 of GeV. So we have a theory where in the low energy scale, we have usually standard model fields plus the new light vector we want to study. And at high energy physics, we have this anomalon fields we supposed to be very. So in cases like this, no. We are considering our UV theory. Exactly. You consider to introduce anomalous fields in order to cancel anomalies, so the theory consistent, UV complete. However, you know that.
It could be also maybe the theory also not normalize the theory. Because if you have less fermions, less speed, then you cannot normalize the theory. So
however, we are considering.
So with fermion, you will be able to cancel the anomaly. But once you remove some field, you can have also normalization. Because your theory and infrared, you can normalize. Infrared physics. Yeah. Can you normalize the infrared physics? It's also a problem.
So maybe put.
The method current is anomalous, but you can normalize.
So you complete the theory with anomalous fields.
No, sure.
A low energy introduce
so the low energy, the theory is
if you want a gauge theory, if you want the gauge symmetry to be conserved, you need something that cancels anomaly. Usually, you want to use a new fermionic field.
The heavy fermions are integrated.
Yeah, exactly. It's what's
you have something Wess-Zumino.
exactly.
Oh, okay.
That's what. Yeah. And we will say that in the speech slide. But the idea is that usually because the anomalous fields are so heavy, you work in a framework with effective field theory. So you integrate how this EV framework fields, and you work with effective field theory related with the fields of the light, the low energy, written with the fields of the low energy physics. And the one of the most important example of effective field theory operator is the Wess-Zumino written term, because the wit term matches the anomalous symmetry breaking due to the presence of the U-free fermions that disappear from the theory when you make effective theory. Now, Wess-Zumino terms are functional of gauge vector bosons and of the constant fields related to the Higgs mechanism that gives mass to the anomalous fields. And WC operators appears every time you integrate out a fermion field, because WC operators are needed to cancel the anomaly you have when you no longer this fermions inside the theory. This answer your question. Okay. And so exactly, what's the real terms transform like that in order to cancel, in order to match the anomaly, the current anomalies of the disappearing UV fermions. And with methods, however, are very complicated objects. We are non-naive mathematical interpretation. There is no expeditious general solution for any individual group. But however, for the scope of our work, we are not interested in evaluate all the complete Wess-Zumino term. We are interested in the Neutrino operators in part of the Wess-Zumino terms, which are those shown in the slide. We are interested on the effective theory coefficients of these Neutrino operators, where HA are the Gaussian fields related to the Higgs mechanism that equals to the anomalous fields. And we want to relate them by simple one loop matching, limit where the anomalous fields inside the loops are very easy to reduce the mass performance in the loop goes to infinity. And you see this general result from one loop matching. I spent like 2 months to obtain this result. So this tells you that Wess-Zumino
of the triangles.
Yeah, only of the triangles.
There is the mass of the
M is the mass of the sum is over the fermion scheme taken out. As you see,
it will be the coefficient of WZ. Yeah, it's like the match something. You figure it out experiment and then
exactly.
Yes.
And as you see, these are not even not simple expression, trivial integration. And however, now still before baryon number leads to it's anomalous. And as an example, if we consider mixed anomalies, where the 3 vertices of the one loop diagrams I showed before, 2 are related to the weak current, and 1 is related to the baryonic current, or 2 are related to the aversion current, 1 related to the baryonic current, with the most vanishing value for the anomalous trace.
This number comes from the standard model of that.
with this is the example, so only some model fermionic fields leads to variation with this anomalous. So, for example, in this case, we need to introduce Wess-Zumino operators in the infrared physics in order to cancel this.
Now the standard model is not effective. The standard model, you can normalize the binary number is not edge.
Yeah, I just make an example. You try to gauge a variant number with only the standard model from fields. You have that the baryonic current is anomalous.
Okay,
so
this will be
if you assume there is something you don't know in the UV physics, you must work with effective field theory, assuming that in the low energy we have some Wess-Zumino operators that cancel the anomalous part coming from the standard model from the fields. Now,
this already is dimension.
These are dimension 4.
Dimension. So usually the longitude is dimension 4.
Yeah, exactly. Because in there is the decoupling theorem, and they say that when the mass of the fermions integrity are goes to infinity, usually you should not see any signals of them in the infrared physics. However, this is not doesn't happen for the Wess-Zumino operator because for physical reason you need to matrix the chiral anomalies of the fermions. So when the mass doesn't matter that the mass of the fermion are goes to infinity, you have the physics must remain the same. So you obtain 4-dimensional operator which are move magnitude and for the mass material going to infinity.
But now the coefficient we see is totally free. We got the standard model plus the.
No, they are not totally free because they need to have the right value to cancel to cancel the standard model. And now
you mentioned
this is an example, and it's partly because we show you the operation, the important operator we are going to study much more, which are the ZWW interaction.
Why this one?
Now I'll tell you. First of all, as I told you before, there are energy enhanced part of the amplitude when light vector coupled to a non-conserved current.
How do you use the black box?
Yeah, it's if you need. No, there are energy enhanced part of the amplitude involving the longitudinal mode of the light vector when coupled to non-conserved current. And these parts of the amplitude are important because since they are energy enhanced, so it means they goes like energy over the vector mass, and we have considered light vectors. So we have considered the mass is more than the energy we are considering. So it's enhanced rates of the due to this part of the amplitude. We want to study only this part of the amplitude. We want to isolate this contribution, which is energy enhanced. To make this, we apply the Gaussian equivalence theorem. So we substitute the vector field with this Gaussian associated mode, which are related to the longitudinal mode of the light vector. So we make this substitution inside the Wess-Zumino operators we see before, and the 4-dimensional Wess-Zumino terms now becomes Axion-like 5-dimensional operators. And the 5-dimensional they grows the contribution to the amplitude grows with energy, and that's exactly the part of the amplitude we are looking for. And because the energy enhanced leads to the strongest bounds.
And also, what is the
this type of operator is
here there is a X,
because this type of operator is to amplitude which grows with energy. Now the interaction between the light vector we want to use the X field and the W field, so it's WW gamma. It's important because W loops use flavor changing error current interaction, where the W loop allows the flavor changing, otherwise we do not have such an error. And the light vector can come to the fermion line directly with the three-level interaction with them, or can interact with the W boson through the effective operator due to the Wess-Zumino operator. And because the effective interaction between the W boson and the X and the light vector is energy enhanced, it's come out that the dominant contribution comes from the first diagram, while the second one is completely subdominant. So we neglect the second diagram. We only consider the contribution coming from the W loop and the Wess-Zumino operator. And we found out that effective FCNC couplings originating from the WC operator leads to meson decays can be tested and observed. This is, for example, an example of collection of experimental balls due to the effect I just told you before. In this case, is considered the case where the UV anomalies are standard model vector-like with standard model vector-like masses. In this case, the paper obtained this expression for the effective FCNC operator, where the constant A is the anomalous trace of the. This is the case of the gauge varying number. You can see all this example, and A is a constant attention. It's the anomalous trace of the fermionic mixed anomalies in the Higgs interaction with only the standard model Fermi fields. They assume that there is not level value for the mixing term by its reducer loop. And they plot these results where or the color region are coming from the bounds from the FCNC interaction I studied now, where the X can decay into visible decays, which are plus minus pair, or more anti-one pair, or can decay invisible, just assuming that there is no, the only visible decays are the modules. And actually, the gray region is the collection of bounds coming from the previous lettering. So they found out that the color region, so the bound is coming from this type of effects, seem to put stronger bounds, stronger constraints on the cabin and the mass of the light vectors, expect that those is coming from dynamics in the coupling or the already studied constraint from the detergent. So it seems that this type of constraints are very important, very strong. So the aim of our work was to answer to one question: how we can avoid this these constraints, which are extremely strong. Well, we consider the crystal dispersion inside the constant of a model of the region of the standard model is that of symmetries, which are the variety number V and the lepton family number. And we consider generic linear combination of these selector symmetries, and we enlarge we enlarge the Abelian symmetry related to this number, the standard model group, and as you know, the only combination of the standard model symmetry, which is free anomaly, is the difference between lepton family number.
Is this like the baryon minus lepton? I think that's sense less than 5.
Sorry?
B minus L.
B minus L.
Anomaly is not completely free anomaly, because without right-hand neutrinos, you can have the gauge symmetry is anomalous. However, B minus L is not mixed anomalies, so a little different. So you are even with only the difference between the lepton number is free anomaly inside the standard model, which means with no right-hand neutrinos. If you add 3 type of right-hand neutrinos, you cancel also the remaining anomalies to B minus L, but you must assume at this point that you are standard model plus right-hand neutrino, which are not so obvious.
That's quite sort of reasonable that assessment. It's like Neutrino wrong.
Right. All right. Generic linear combination with standard symmetries is anomalous, and the mixed number proportion to this combination of the linear coefficients, which are related to some B plus L symmetry, just because B minus L, which is actual to B plus L, is not anomalous when you consider X anomalies. It's anomalous already. B minus is normal as anomalous like when you B minus L to the third. Only those that type of anomalies, which are, however, you must consider with the right-hand neutrinos or in the HDA conserved. So for our model, once we want to gauge the accidental symmetries, like generic measures of anomalous symmetries, we must introduce anomalon concept. Our choice is this pre-content, where the anomalous charge under the electroweak group are needed to cancel the mixed anomaly free. Yeah? And we insert also right-hand neutrino to cancel UX and UX cube anomalies, where the coupling on the U1 charges of the right-hand neutrino, which try to do this version shown in the slide. And then we added a single field in order to give mass to the Higgs boson, this new anomalous symmetry. So we choose our anomalous field to be vector-like under the electroweak Higgs group, which we choose the UV charge, U1 charges that we can also to be like to allow the chiral masses coming from this mechanism where H field are vanishing level. And this is an important requirement, as I will show you later, that mostly-chiral anomalous are the solution of the problem we are looking for. And however, depending on the U1 charge of the S field, one can also have anomaly vector-like masses for the anomalous fields coming from the of the single Higgs field. So we have the anomalous fields can have masses from two different distributions. As you can see here, the U1 charges of the anomalous fields have two non-specified free charges, which are related to a global symmetry of our model, corresponding to a sort of a weak anomaly number, corresponding to a replacement of the weak anomalous fields. And this global symmetry is not our requirement, so it can be broken by additional Yukawa terms or specified values of y and its values. However, we start with our theory with free charges, and we should later that depending on we assume new Yukawa terms or not, we have two different types of phenomenology, because these additional Yukawa terms allow mixing terms between some anomaly-free field and a new anomalous field. So I talk about this at the end when I talk about direct symmetries. Now, this model, even if not the point of our work, can give rise to Dirac-Majorana type of masses for the neutrinos. And if the value of the single Higgs field is large enough, our model produces a system mechanism to give a small mass to the left hand and the neutrinos. We so our model should be able to explain the problem of the masses for neutrino. However, we didn't made all the calculation to see if our prediction is according with the actual experimental value. So because it was not the point of our work. Now, the point of our work was about the FCNC interaction, how to avoid the constraints related to this. Now, we recalculated the effective coupling of this interaction, and we calculated the W0 coefficients related to this interaction, which happens to be not more fixed, like in the case of the previous example, but it's still done by the parametric angle, which is given by the relation between the contribution to the mass from the H fields and the contribution to the mass from the H field. And depending on how the anomalous pick up mass is from H, from S, or for both of us, the coefficient, the coefficient acquires a different value. We found out that when we say that the Yukawa coupling of the anomalous field to the at weak Higgs field is 0, so they have a standard model vector-like masses, the W0 coefficient is exactly equal to the anomalous trace of the mixed anomalies. And in our model, the anomalous trace of the mixed anomaly we assume is non-matching. So there is no way to avoid this bound. So with standard model vector-like masses. However, at the opposite, if we consider mostly-chiral anomalous fields, we obtain that the temperature efficiency is vanishes. So we obtain that mostly-chiral anomalous field leads to harmless Wess-Zumino terms. So the energy enhanced processes coming from the emission, the neural models like that, completely disappear. And this is the solution we were looking for. So we we conclude that mostly-chiral anomalous fields could leads to the selection point of the temperature of the field, so that we cannot strong coupling subconsider from that. Now, our solution is that we must take mostly-chiral electric anomalous to be safe from the strength coming from the terms. However, if the anomalies can have a pickup mass from the electric field, we should see a signal from them in the Higgs decays. And especially in the X to gamma channels, we know that the experimental results is according with the standard model prediction. So if we assume there is new physics contribution to this decay channel, we must, however, obtain a prediction which is a standard model. And the only way to make this is through a sort of magical cancellation between the amplitude due to new physics and the amplitude of the standard model coming from the standard model. So we assume that the new physics amplitude to this decay channel is equal to minus twice the amplitude of the standard model light. In this way, the prediction to this channel is standard model like, and we can be in accordance with the experimental limit. Now, we know that when we build the amplitude coming from the normal fields in the limit of large matrix, the normal contribution depends only on the y parameter, so the free charge of our model. And we found out that if the modulus of y minus 1/2 is close to 3/2, we have that our mathematical prediction is standard model like. So it's in accordance with the experimental limits. However, we are not able to make this major consideration for all this particle. We choose to make this major consideration from Higgs to a gamma decay channel, while we make a theoretical condition of a large deviation in the Higgs signal in the gamma zeta decay channel of the Higgs particle. And this deviation can be is not completely our problem because this signal is not pretty well measured until now, and so it can be tested like in the phase or election. So our prediction is not pretty good so far. We must expect the first result of high-luminosity phase. Now, searches of new anomalous. Now we must distinguish two cases. If you assume that y the minus y minus 1/2 is close but not equal to 3/2, we cannot have a dictionary Yukawa tensor because you're sure. And so there is no mixing term between electric anomaly and standard model fields. This means that if we take the light lightest state of the electroweak anomalous, this is stable because it cannot decay into all standard model light because of the global symmetry of our model relating to a sort of electroweak anomalous number. So we have a fermion which is electrically charged and stable. So makes some problem from a cosmological point of view, and need to invoke low scale inflection to permit this scenario. And however, stable charged particles will stay continuous colliders, and the actual experimental limits we found in the literature coming from CMS that puts that the mass of this fermions could be above 800 GeV. This is the actual experimental limits we found. In the other case, if minus y minus 1 alpha is equal, exactly equal to 3 alpha, we can write additional circumstances that allows electric anomalous to decay into only standard model states, so that there is no longer an anomalous field which is stable. All of them decays in standard model leptons, and we didn't find the estimation of the actual experimental limits in this scenario. However,
but it's that stable. Then you are making also by the map that symbol is unstable. It's not unstable.
I mean, it's going to
density. Start you up exotic leptons. The quantum number, the chapter,
just not, sorry. Saying that we will find out exact estimation of experimental limits for the case of stable anomalies. However, reading the literature, we found out that the bounds should be in the same order of those obtained in the case of stable charge leptons. So our experimental limit from coming from the direct structures of new anomalies is about 400 GeV. This means that since we are considering mostly-chiral anomalies, such as so anomalies that pick mass from the H field, we know the values of the value of the H field. We have the Yukawa campings of this new anomalous field are extremely large. We are on the boundary of the perturbativity.
With the, I think there's a thing, the modal experiment so I think one of the things it can look for is it's like massive, stable charged particles. Would that be relevant to any of the limits? It's designed primarily for magnetic monopoles, but stable, heavy charged particles would also track that, well, sheets of plastic. Poles.
To believe the experimental is larger than this we found. So cannot transfer at the moment. I will think about it. And so just a summation of what I told you in this talk. And, this is the end of my seminar. Yeah.
So the next step is the X to follow Z.
Yeah, it's very big. Our model is if complex film that the result is a model-like and models excluded. To be honest, our model we make.
Yeah, they're not the models. No, this is just the fixed.
Yeah, the honest thing is that our model requires mostly-chiral anomalies, so means that the chaos this anomalous should be very large. This means that I go the correction to the prediction of each to the gamma should be consistent, should modify the simple prediction, simple analysis we made for X case. So our model works, but at some point to be clarified.
All right, no one else has is the directional link function stable in this model? So there's a extra fermion coupled to Higgs, and it's Yukawa very large. So the gradient correction Higgs potential is the study one. Stable.
If the
Monorail coupled to Higgs in if Yukawa is very large.
Yeah.
Therefore, it's like top Yukawa correction Higgs potential is not right, but Yukawa is very large. The electron function stable.
Yeah, this is another point that we didn't think about our we work this model. I assume yes, new fermions with large Yukawa will impact the stability of the Higgs vacuum. Or we didn't work about it. This was not the point of our work. We just used this model as example of how to avoid the from the Wess-Zumino term. So we didn't think much on some other direction. This is the first work we made on this model. We constructed it for different reasons. We think that this model would be viable and interesting model. We made some more complex analysis as the one you just suggested.
All right, thanks, Claudio, again.
It's all. That's the